This is part 2 of buffers. Let's talk about how buffer actually works. So remember that buffer is a solution that prevents pH drastic changes even if you were to add small amount of strong acid or strong base in. Here's an example of the acetic acid and acetate. So in solution, the acetic acid is like this and its conjugate base looks like this. So the conjugate base has a negative charge, whereas the acetic acid in itself already has hydrogen attached. So they're both weak acid and conjugate base pair, and so therefore they are considered to be a buffer solution. If I were to add a strong acid such as HCl, what would happen? Well, the HCl will definitely split apart into two since this is in water solution. So imagine there's water all around, and this will split apart. Having this being a very strong acid, what it's going to do is the hydrogen will become donated to the weak base. So say more HCl has been added, the hydrogen will interact with the weak base, forming into an acetic acid. So here is my next showing. It shows that it has been attached to these guys. The chlorine, there are, remember, the spectator ions, so therefore they're sort of floating there. They're not really doing much. So if I were to put this in a formula equation, we can say the hydrogen ion, or we can even put hydronium ion, H plus the conjugate base, the acetate, goes into forward reaction where it's going to form a acetic acid, so which means it has a H attached. So because this H is being attached to these guys, the pH that measures the pH is negative log of the concentration of H plus or H3O plus is the same thing. And because it's supposed to measure this concentration, well, as soon as it comes in, it's going to interact with the base. So we don't have H pluses hanging around. Because we don't have H pluses hanging around, it doesn't affect the pH. Let me give you another example, but now with the strong base, such as sodium hydroxide. When sodium hydroxide is submerged in the solution, it will split off into sodium and then hydroxide minus. Now the hydroxide minus is going to want to receive the hydrogen from its surrounding, and it's going to target this one. The acetic acid is going to donate it to the hydroxide to form water. So say more sodium hydroxide had come in, then the hydroxide and this hydrogen will form water. So if I were to show that in this image in the next box, you'll see that water, HOH, has been formed. That OH comes from the sodium or sodium hydroxide, and again here sodium hydroxide, and sodium is just hanging around. These are my spectator ions, meaning they don't participate in the reaction. So is chlorine spectator. So if I were to rewrite this in a chemical formula balance equation, we can have hydroxide with the acetic acid forming into its conjugate base form and water. So HOH is H, same as H2O. So this is equals to H2O. Okay, I just wrote it in this convention just to show you where this H is coming from. This H is coming from the once was an acetic acid. So you can see in the beginning, you might have say equal amount of the acetate and equal amount of its conjugate base. If you were to add acid, what happens is the amount of the acetate starts to increase because the H is being donated to the conjugate base. Whereas if I were to add in hydroxide here, then that will pluck off the hydrogen of the acetate. That will drive the acetate to increase and where acetic acid to diminish because it's going to take the hydrogen from here. So that's how sort of like how buffer works, and it prevents for the pH to recognize any hydroxide or hydronium ion present because there have been already interacted with the weak acid and the weak base, and so the pH does not change. So think of it as like this. Say if you were in a circus and you're the guy who spins these plates and they're all well balanced and this plate represents pH. Well, no matter how strong of an acid wind comes, okay, if there is a trusty assistant like this weak base assistant, it's going to prevent the pH from diminishing quickly. Whereas if there was a strong base wind to knock down the pHs, then there is your trusty assistant, the acetic acid or the weak acid that prevents the pH from increasing drastically. So something to really note about buffers and adding strong base or strong acid when we do some problems, you're going to always think about that these reactions go into completion, meaning that we have this solid arrow that goes into the forward direction when we're used to going into forward, and the reverse direction when we used to talk about equilibrium. But this is not, we're not talking about equilibrium. This is us going into full completion because you're adding in a very strong acid and strong base. It goes into a final state. So we're not going to be using the ICE table, but we're going to change its name to ICF, and F will represent the final. So I represents initial, C represents change, and before the E represent equilibrium, but now not at equilibrium, F just meaning the final, what happens in the end. Consider the solution with 50.0 ml of 1.5 molarity of hydrofluoric acid and 30.0 milliliters of 0.80 molarity of potassium fluoride. What is the pH of a solution of 14.0 ml of 0.90 molarity of the strong acid HCl is added? So we have this buffer system of hydrogen fluoride, hydrofluoric acid, and we have our fluoride ion. And that's because I put F minus because this is our spectator. Potassium is our spectator, so we don't consider that part of what we're going to solve for. Now it's asking for, hey, we have this buffer solution filled with HF and F minus. Okay, now I'm going to be adding a strong acid, HCl. And so now what is the pH change? Well, the pH in the beginning, if you were to recall from the first learning check in part 1 of the video, well, the pH initially was 2.67. Now that you have added the HCl, a very strong acid, in this buffer solution, what happens to the pH again? So we're going to have to look for what is this acid going to react with. Remember this strong acid, by definition, that one of them is a spectator ion. So which one would be a spectator ion? Hopefully you were able to identify that chlorine is the spectator ion and the hydrogen is the one that is going to be acting as an acid. Chlorine is not a base. Okay, we don't consider that as a base and trying to pluck out hydrogen, because remember that if you have a very strong acid, only one will go into reaction, the other will be a spectator. So we have H that's going to be interacting with something. So we have hydrogen interacting with what? Which is the acid, which is it going to act with the weak acid, or is it going to interact with the base? So acid will always interact with the base, which is F minus. And so this will form into HF. Now, why is this important to set up? And this is because we're going to be utilizing the ICF table. ICF table not in molarity, but rather in millimoles. We're used to having this in molarity. Also, we're used to having, instead of F, we usually see E representing equilibrium, but because this is a very strong acid, it's not going to form an equilibrium, but it's going to react into completion. All right, so what is this millimole business? Well, whenever you multiply milliliter, some type of milliliter, multiplied by molarity, molarity is that big M, and that is represented as moles over liter. Your previous instructor probably have told you mark this wrong because you have milliliters on top and liters, when it's supposed to be liters and liters, or milliliters on the bottom. But because this is a little different, we're going to go ahead and take out just the L, the liter. So therefore, you would just get millimoles. It sounds complicated, but I promise you the concentration calculation will be easier if you were to utilize millimole. All right, so based on this, let's find the millimoles for hydrogen, fluorine, and HF as well. So initially, in the very beginning, we have hydrogen with the hydrogen, which is coming from the strong acid. So with strong acid, we have 0.90 molarity. And how many mLs of it? Well, you have 14.0 mLs of it. So moles over liter. And you're going to go ahead and cancel out just the liters, and you're going to multiply the 14 times 0.9. That would give me 12.6. So this is my 12.6 millimoles of H plus. So I'm talking about H plus here. So I can plug this in here, 12.6. What about for F minus? Well, for F minus, which is coming from this information up here, that's 30.0 ml times the molarity, 0.80 moles over a liter. So the liters could cancel, and for millimoles, I would get 24. So 24 millimoles. This is for F minus. Now for final HF. In the beginning, initially, we had this much amount of HF. So we write 50.0 times 1.5 molarity, or moles over liter, and the liters could cancel. $75, yeah. So I get 75. So if I were to go into completion, you're going to look at the smallest value first, which is the 12.6. That's going to be your change. Because the reactant is forming into a product, we're going to subtract 12.6. That means this also 12.6, but here we're going to add 12.6, okay? Well, in the end, you would get, then if you were to add the top and the bottom, top and the bottom, top and bottom, top and bottom, if you were to add those two numbers, what number final would you get? You would get 0 millimoles. For here, you 24 minus the 12.6. You get 11.4. These are all millimoles. And if I were to add the top here, this would be 87.6 millimoles. Okay, 87. Yeah. Okay, so now that we have this so far, we're going to go ahead and calculate out the molarity. So we're going to go back and calculate the molarity of all of this. Well, we know that molarity of all of this is moles over some kind of liter. Okay, so we have somewhat of a mole, but what about what liter am I going to use? Well, underneath the here, you're going to utilize the total volume present in this entire system. Well, the total volume in the system is 50. So total volume is 50 ml plus the 30.0 ml plus the 14.0 ml. And you should get 94.0 ml. So I'm going to put 94.0 ml. And the M nicely cancels out, and now you have just moles over liter. So now that you have moles over liter, so let's calculate this out. 11.4 divided by the 94.0. Now we get 0.12 molarity for fluoride. What about for HF? So divide this whole thing by, so let me put a box here so we can separate 94.0. That's the total. We can cancel out the milliliters. And I would get 87.6 divided by 94.0. Get 0.93 molarity of HF. Okay. Now we haven't even gone to the acid. We were looking for pH, remember. Now what about concentration of this one? Well, if I were to divide this whole thing by 94.0 ml, you would just get 0 because there's nothing left over of the strong acid. So how do we get pH of all this? Remember the Henderson-Hasselbalch equation. So I'm going to put that on the corner in a different color so we can distinguish. So Henderson-Hasselbalch equation is pH is equal to negative log of Ka, or pKa, you can say. And let me write this as pKa, plus the log of the base, the conjugate base over acid. So we have negative log of 6.8 times 10 to the negative 4. That's your Ka for HF, plus the log of base, which is right here, 0.12. And the acid is 0.93. Okay, let's plug this in. So we have negative log of 6.8 times 10 to the negative 4. Press enter, and then I'm going to add the log of 0.12 divided by 0.93. That will give me 2.28. That's my new pH. So what does this tell me right here? If you recall from learning check, the very first learning check in part 1 of the video, when we had just the buffer before the strong acid has been added, so before anything has been added, the buffer system had a pH of 2.67. Now we added the strong acid, and now it has dropped to 2.28. So if you can see that there was a slight drop, but not significantly. When you add a strong acid, it drops like 2, 1, 0 very quickly, but you can see that with this small amount of acid being added, the pH change was very minimal. Now, what will happen if you were to add a strong base? So I'm going to set this up a bit and then you will find out the pH on your own. So consider the same solution as before, but now what is the pH of the solution of 12.5 ml of 1.20 of a strong base has been added? So say in a solution you already have HF and F minus, okay, floating around. And now you are adding a very strong base in here, okay? Initially, your pH was 2.67, I believe. No, quickly checks. Yes, 7. Okay. Now I'm adding a strong base. What is my next pH going to be? Okay. So probably will increase because you are adding a base, but how much are you going to increase is the next question. So we're going to set up an equation and we look at the base first and we determine which one is a spectator ion and which one is going to participate in the reaction. So we know that sodium is a spectator ion, so we're going to take that out, and so we have a base. We have a buffer solution with HF and F minus. Which one is it going to interact with? So here's my base. So it's going to act with the weak acid instead of the weak base. So it's going to interact with HF, forming into, so because it's a base, it's going to accept the hydrogen from the HF, so it's going to form H2O and then plus F minus. Now we set up the ICF table, and this is all going to be in millimoles. All right, so what you're going to do is find out the millimoles for all of these participants, the hydroxide, the HF, the not the water because we don't need the water because this is liquid. All the aqueous will form, and HF. Okay, so we don't need this one, but everything else, try to find the millimole initially and come back and check. So here are all the millimoles, and we select the smallest millimoles in the reactant side, which is the 15. So we're going to subtract 15 for all of these guys. Subtract 15. But for here, for the product side, you're going to add 15 because we're forming into the product. You'll notice that there's a single arrow because it's going into completion. You're going to add the top and the bottom. So 15 plus the negative 15, that would be 0. 15 plus the negative 15 would be 60. And then you have a 24 plus the 15 will give you 39, okay? And these are all in millimoles. Now I want to divide that by the total volume on the bottom here, so that we can get the final molarity concentration. Well, the total volume is 50.0 plus 30.0. These are all in ml, plus the 12.5 ml, and that equals the 92.5 ml. So here, 92.5 ml, 92.5 ml. And if you were to calculate this out, you should get molarity of this one to be 0.65 molarity and this one to be 0.42 molarity. Okay. If this is too fast, pause and then try it yourself. Then what do we use to find pH? Hopefully you are able to say the Henderson-Hasselbalch equation, which shows the pH is equal to pKa plus log of base over acid. So we're going to go ahead and plug all these values in here and then come back and check what the pH would be. The final pH is 2.98. Well, initially the pH was 2.67. Now that base has been added, it's 2.98. There has been a change in which the base allowed the pH to rise, but not too high because it's in a buffered solution.